Hello everyone, and welcome back to a new episode of Advent of Code. We're here today to do episode 8, and this time I've already done the solution off camera. It was just not very convenient to record it. So instead, you guys are going to get what usually happens in such cases, a tour of the solution, how I arrived at it, explanations of some points on the way that I thought were important, and so on. But let's go ahead, of course, and start with the problem definition. Day 8. I heard you like registers. You received a signal directly from the CPU. Because of your recent assistance with jump instructions, it would like you to compute the result of a series of unusual register instructions. Each instruction consists of several parts. The register to modify, whether to increase or decrease that register's value, the amount by which to increase or decrease it, and a condition. If the condition fails, skip the instruction without modifying the register. The registers all start at 0. The instructions look like this. So they have like a register, a thing to do to it, how much to do, so increment or decrement are what these are supposed to mean, how much to increment or decrement by, and the numbers can be negative, so this is like obviously redundant. They don't, if we support negative numbers, it's kind of silly to also support both increment and decrement, but okay, whatever, it's a made up CPU. But every condition has, every instruction, I should say, has a condition. So only do this if this is true. And there are no jumps, there's just increments and decrements. We start at the top, go all the way to the bottom, and see what happens. And it mentions somewhere that all instructions start at 0, or all registers, yes, okay. So all registers start at 0, and we are asked to find out what is the largest value in any register after running the whole program. And it mentions that there are all 6, the comparison operators you're used to seeing: equal, not equal, less than, greater than, less or equal, greater than or equal, and so on. Not a huge surprise. So let's now look at a solution to this problem. Of course, we have this. And so I guess let's skip over the imports and why I think I need these functions from map and bool and list and so on. And look first at the stuff under this, the types. So obviously this is a pretty simple data structure, right? And if we wanted to, we could easily just use a tuple of size 6 to store these 6 things, right? All the 6 things we need to know about an instruction. There's, there's 6 fields, right? What register, what to do to the register, by how much, what to test against, how to test it, what size to test that against, and so on. So we could just have a tuple of size 6. Haskell supports those, no problem. But it's not very clean, right? Haskell encourages you to define types for your values so that you can write more clearly about what your program means, and so that Haskell can help you when you write something that doesn't match with what you said you wanted to write. So to that end, the first thing that I did was I defined a line type. It's no longer here. I wrote something like data line equals line register op amount int, and then another register and like a test and an int or something like that, right? This is isomorphic to a tuple, but sort of a little bit better in that it gives you, it's your own type, and you can say this isn't just a 6 tuple, it's a line, and this is the data we got from parsing this line, whatever. So I did that, and then I was like, this is silly. Really, an instruction isn't 6 things, it's 2 things, right? A mutation that we want to apply to a register, and a condition under which we should decide whether to do it. And I don't know, this is something that sort of guides how I design programs that I remember, like, when you're writing software, like, the whole world is malleable, right? You can do pretty much anything you like. The computer is happy with all sorts of nonsense, but a lot of writing programs is about expressing to humans what it means, and also about, like, if you have a model in the computer that matches closely the way that you think about the program, about the problem, I should say. If you define structures inside the computer that reflect how you think about the problem, then it'll be very easy to abstract over the things that you're trying to work with. And so one thing that they talk about in SICP is that it's, say, structure and interpretation of computer programs is not passing around, like, don't define a function that takes two arguments x and y if it's a function for, like, operating for like a point on a graph. The example that they give is, like, ratios, right? You could define a ratio as, like, it's supposed to be a numerator and a denominator, and all the functions that take ratios take two arguments, one of each. But it just, like, kind of sucks because it means you can't make a list of such things. You can't. It doesn't compose very well, and so I try to find logical groupings and squish them together as much as I can. And this is not, like, revolutionary stuff. Lots of people do this, like, without even thinking about it. But it's just something I wanted to point out is that the natural, like, the input line has six elements. Let's find a data structure with 6 elements. That would be fine, actually. I wouldn't even disagree with that, so long as your next step was to transform a line into something with just 2 elements. Because I think 2 elements is sort of the platonic ideal of the thing we're working with here, a mutation and a condition. Anyway, so all of that is a lot of verbiage for, this, which is not really very much. But, like, I don't know, you guys watch this to hear me ponder about philosophy as much as about to watch me struggle with algorithms. So the other thing is we need, of course, types for the mutation and a condition. And they're relatively straightforward. We're using reg here to mean register, and as you can see, I defined register to be a type synonym for string. The difference between type and data in Haskell is pretty large. Data is for defining a new data structure that holds, 0 or more things, whereas type is just giving a new name to an existing data structure. So, if it would be, I could do this, and none of the rest of my code would need to change, because it's like string and register are literally exactly the same thing as far as Haskell is concerned. We give it this name, just to let us say, oh, this is a register. It's not just any old string. And we could be more strict and cause Haskell to enforce that, but by using a different mechanism. But type is a pretty lightweight thing that helps make your data types more legible without actually changing the runtime representation of them. So anyway, we have a condition that takes a test and an int. Now, here I've defined test as a type synonym for a function from 2 ints to bool. Actually, let's look at op, because that one is simpler. Op is a function from int to int that returns an int. I had started out first finding data op equals inc or dec. And then I would parse a string that was inc or dec into an op, and then I hadn't written it, but I was going to. I would have a function for applying an op to 2 ints, which would switch based on whether the op was inc or dec. But I think that that's sort of like, it's not wrong. It's representing things in a more abstract, domain-specific fashion, I suppose, where the domain is like our problem. If we use this representation instead of this representation for an op, we're keeping ourselves further from the Haskell runtime and closer to the problem statement. And there's not necessarily anything wrong with that. We might have found, for example, that part 2 says, oh, actually, everything that says ink is supposed to say multiply. Sorry, we typed it wrong. And, like, you could do that with an op. You could just change how you interpret one of them. Where with this implementation here, we could say, oh, I'll just change the interpretation of ink. Easy. In part 2, for example. With this solution, we couldn't really adapt to that very well, because a function type is opaque. You can't inspect it to see, is this a plus or a minus? Like, is this ink or deck? It's gone by the time you get to this representation. But I don't know. So I decided it was worth the expedience of just storing a function, but I might have been proven wrong if it had been important to go back and change decks in part 2. Anyway, so we have these mutation and condition variable thingy or types that each hold 3 smaller thingies. It's all like pretty straightforward, and honestly, like the majority of code in this entire thing is just the parser, which is a very simple parser. It is not complicated. It just like has a lot of cases. Apparently, in a lot of other languages, such as like Python, or if I were doing this in Clojure, I might consider using eval. Although I really don't like eval, and I probably would not. I would do something very much like this, even though in Clojure it's not necessary, whereas in Haskell it really is. Anyway, in Python or say Clojure, you could just like read the string right angle bracket and eval it and get like a function right angle bracket or something like it, I guess. Get the function greater than. But what we do instead is first I say parse, which takes a list of string, all the tokens on the line, and we just give them all, bind them all to variables by pattern matching. R1 and R2, the op to use, the amount to op by, the test to use, and what to compare against. And we say build an instruction where the mutation is R1, and the amount to mutate is reading the amount, and op is this op apostrophe thing here. And we do something similar for cond, right? Pass in R2 and read compare, but then call like test prime. And that's sort of like just a Haskell idiom, is if you have another variable that's like an upgraded or newer version of a previous thing, you just name it with a prime symbol. And then we define these in the where clause. And it's pretty simple, right? We say, well, how do you parse a string that is either ink or deck? You do a case match on it, a pattern match. And if it's ink, you return the function plus. And if it's deck, you return the function minus. I don't know if you guys have seen minus and plus operators treated as like bare functions yet. You've seen an operator section like actually, let me just get out a REPL. That'll be easy. So, like, if we say let f equal times 5, we can say f of 10, and we get back 50, right? And I talked about how operator sections like that work with partial application and currying and so on. But you don't even have to supply any arguments. You can just say let g be the function multiply, and then we can say like g 10, 20, and we get 200. So that's what we're doing up here, is we're just saving all of Haskell, saving a reference to one of Haskell's built-in functions based on the operation that we get. And likewise for test. The only slight twist is that we don't use bang equal, we use slash equal. That's the Haskell word for not equal. But overall, parse is extremely straightforward to take a list of strings and produce an instruction. Now, the other type that we didn't look at earlier is this regs type. It is so how do we represent the registers in our computer? If we were crazy, we could do it, for example, as a list of tuples, where I say crazy, people used to do this like all the time in the olden days, I guess you could say. A list of tuples where the first part of the tuple is the key and the second part is the value. And anytime we want to look something up, we would just scan through all the registers until we found one with the right name, and then look at the associated value. You know, it's possible. You could do that. But the natural thing is to use a map, specifically a map from register name to register value. Simple, right? So I call this regs, so I don't have to keep typing out m.mapreg_int over and over. Just give it a type alias. And so our... Let's actually just put that stuff at the bottom out of the way. Sort of the fundamental building block of running a whole program is running one instruction, right? After you've done that, everything else is just gravy. So we need a function from a register set and an instruction to a new register set. And I don't know, is this the best way to have implemented this function? It could be, maybe. I don't know. It's a matter of taste, I think. So we have apply it takes two arguments. The first one is the registers, and the second one is the instruction. And of course, we just do pattern match against all of the fields in the instruction here. It would be like if we had used the line with the 6 arguments, this would look pretty much the same, except we wouldn't, like, we'd have line here and we wouldn't have these wrapping things. It would be shorter. But I think that it's just, like, not a good representation of our reality to do things that way. Writing a program is like modeling the universe, and I think that this is a better model, even though it doesn't lead to any obvious gains in the source code. So, fine. Now that we've pattern matched apart all the pieces of the instruction, what do? We call this bool function, and I'll get to what bool is later. I want to start with get, which... So basically, maps have a... You know, how do we look up the value of a thing? Of a register? Well, we look it up in the map, and we say, if it's not there, please give me back a 0, because registers are supposed to start initialized as 0. So that's all like pretty straightforward. We could have just written, we could have inlined get. We could have written this. The order would be a little bit wrong, I guess, but we could say, I guess R would go here, and then we could also do in the other place where we call get, we could say that. You know, that's fine. That is a possible implementation, provided, of course, that you get rid of this. But it sort of clutters things up, doesn't it? Like, you're trying to read the algorithm for how to apply things, and you keep getting distracted by this find with default 0m, and it's like you could kind of miss the R in there, right? And you might forget what you're in the middle of doing. And so it's just sort of nice to take... this undo tree takes forever. To just define a little helper function for making the... making it as low overhead as possible, as low visual overhead, as low mental overhead as possible to get a thing out of the map, so that then you can read the algorithm. You know, what we're calling some weird bool function or whatever. Again, get to that later. And what we're calling it on is get R tested against the target. Very simple. Whereas if when we were using find with default directly, it's a little bit messy. And likewise here. M prime, the new map, is insert into, or insert at the key W, the result of getting W and applying the function amount to W and amount, and put that into M. That's enough like words already. It would be worse if you had to like read find with default and so on. So concision is a virtue, I suppose. So, by the way, I call these W and R because we're writing to one register and reading from another. You have to actually read from both of them, but there's one that you are sort of primarily writing to. It's the one you're mutating. So I figured W was a good mnemonic for that. Anyway, so finally get to this bool function. What is the deal with that? Bool is sort of an interesting function. Actually, let's be... what's the deal with bool? Said Jerry Seinfeld when he was learning Haskell. So bool is a function that takes two values of some type, A, and a Boolean, and returns another value of type A. This is the way that you can avoid... So this is sort of like a function that will pattern match against a Boolean for you, basically. If the bool is false, it returns the first A, and if the bool is true, it returns the second A. Now, like, is this really so amazing? It's not exactly, right? You could just use if-then, or you could do case match on the bool yourself. But bool is one in a family of functions. It's called a catamorphism, and maybe in some future episode I'll get more into like why are catamorphisms interesting. It's something I only recently figured out myself, like what the heck is the deal with catamorphisms. But I think that it's sort of, you know, you saw some of the other ones I wrote. I'm perfectly happy to use if then and so on. But I think that here we sort of want to make it clear that we are choosing between M and M prime by putting them right next to each other and next to the bool function. If we instead wrote, you know, let's say I did this, equals if get our test target, then M prime else M. Like, yeah, that's possible. You could do that. I don't think it's better. It really emphasizes, I think, the test, right? It says we're testing something, and then we'll, like, do something about it. But I don't think that that is how I view this expression. Like, I don't know. Today's sort of a philosophy day, I guess. I view this expression as being much more about choosing between the old map and the new map based on the test, rather than do the test and decide whether to use the old map or the new map. I guess those like feel very much the same when I say them out loud, but I think it's, I don't know. It's nice to have these two right next to each other with a bool signaling to you like, hey, these are the two things you're choosing. If then else is just a little bit tacky in Haskell, I guess. There's so many better alternatives most of the time. This is one, pattern matching is one. And the nice thing about bool, of course, is you can partially apply it. Like, if you have, say, a list of booleans, and you want to transform each one of them to either A or B, you could map bool of AB over your list of booleans, which is kind of cool. Anyway, so that's what this is all about. We're performing the test and using either the original map, i.e. without modification, or the new map, i.e. after inserting at the W a new value. And so now, finally, we can get to part one, which is saying, it asks us, please run the whole program, and then which register has the largest value at the end. Or rather, what is the largest value in any register at the end? And we haven't looked at any folds yet, I think. So I guess I will spend some time explaining what is the deal with a fold. Folding is a very fundamental concept, really, to functional programming. Because everything in functional programming ends up being done with recursion, right? Let's see. Maybe I'll just go to, like... I want a scratch buffer to, like, write things down in. I guess my scratch buffer is fine. I just have to switch to Haskell mode. So let's say we wanted to take a list as input and produce a new list that has all the elements doubled, right? Or in fact, let's be a little more general. Let's say we want to implement the map function. Map takes a function from A to B and a list of A and produces a list of B. And like this is all pretty straightforward to write. We can write map f of nothing is nothing. Map f of x's is fx cons to map fx's. Right? We can write that. It's not hard if you've done it a couple of times. And like this is recursion, right? Map calls map. How lovely. But it's kind of like this is a pattern you do all the time. What if we want to write filter? Filter f nothing is nothing. Filter f x x's equals. I will use bool. Haha, bool. Bool of. Let's see. More or x cons to more applied to fx, where more equals filter fx's. Something like that, right? And it's like kind of repetitive, this pattern match against nothing, pattern match against breaking it up, have a base case, have a recursive case. It's not like a ton of fun to write this over and over. And so it turns out that a fold is a way of abstracting over this thing so that you can just write the novel part of your new function. So fold R is the first fold we're going to look at. Fold R f nothing equal, oh, whoops, we need an accumulator, which, what is the argument order for fold R again? I guess it should take the init. Yeah, so fold R f init, we'll spell it out. Init xx's equals f, well, xf, we'll do it this way. Fx applied to f of x and fold R f init x's. Now, there are better ways to implement fold R, but this is the one that is the sort of most clearly a mirror of what we were doing up above. So fold R is very general, and the cool thing is you can use you can use fold R to implement a ton of this recursive stuff. You can just say map f x's equals fold R what exactly? Fold R lambda of x more to f x cons to more x's. There we go. Can I explain how this works? Sure, I guess. Fold R basically abstracts over the pattern matching and breaking things apart, and just we give fold R a folding function when we're calling map, which basically represents this, sort of, right? You see how we have an fx cons to something? In our original definition, it's cons to map f of x's. In fold R, it's cons to more, which is the second argument fold R gives you. Basically, fold R calls your function with the current element of the list and the result of folding up the rest of the list recursively, which is like magical. that it can do that, but it can because of laziness. How nice. And so we can use that to build, you know, pretty much any recursive function consuming a list. You can write it as a foldr, although it may not necessarily be so clear. Any recursive function that consumes as input a single list, you can do that. You know, it's for filter. It looks similar, but I'm not going to write it out. So it's sort of, you can imagine foldr as folding things up from starting from the right side of the list, right? Because we're looking at more, and like we use our initial value when we finally get to the end and find the list is empty. There's another fold called foldl. F init, and we'll just define it here. And actually, it's not usually called init now. We would call it accumulator equals act. Oops, f act empty equals act. Yeah, foldl f act x x's equals. Wait a minute. Oh yeah. I got confused. I thought I had defined foldr wrong, but I didn't. I was just looking at the definition of map and thought it looks like a wrong definition of foldr, which is definitely true. Equals fold L of f act x x's. So this sort of folds up, it builds your function starting from the left side of the list in a way. We can, if you like, think of foldr f 1, 2, 3 is like sort of the same thing as 1 f2 f3. We sort of replace, actually it's going to be more clear if I write 1, 2, 3. Like so. We're sort of, you can look at a list as these con cells, right? 1 cons to 2 cons to 3 cons to nothing. And we just replace each cons with an application of f, and we replace the empty list with an application of init. And we do something very similar with foldl. We just sort of like do it differently, I think. So we basically, in this case, foldl f init 1, 2, 3 empty equals f of how many f's do we need? 3? Probably 3. Yeah. F of init and 1, 2, 3. So you can see how this one sort of looks like it's left biased, and this one looks like it's right biased. Anyway, the point is this. So foldl, if you've worked in, say, Python, is basically the same as reduce. Yes, it is called reduce in Python. In Ruby, they call it inject, I think. And foldl tends to be more useful in eager languages that don't have laziness, whereas foldr tends to be more useful in lazy languages like Haskell. There's some back and forth, but you know, that's a rough generalization. Anyway, so back to our part 1. Basically, we have a list that we want to process recursively, the list of instructions, right? And we want to, at each step, update the current state of the world. And that's exactly what a fold is all about. You consume one element at a time from the list, and you update your state every time that happens. And at the end, what's your final state, right? We're using foldl prime here, which is basically the same thing as foldl, except that it's almost always better. It's a little bit less lazy about how it treats its function arguments, and that's typically what you want from foldl because it doesn't really work lazily the way that foldr can. So basically we just fold the apply function that we defined above, starting with an empty register set, over the program. And like by magic, what we get out at the end is the final register set of the program at the end. And so part 1 is very easy to solve from there. We just take the final register set, we say what are all the values, what's the maximum, done, right? And of course, you know, we do get 4,888 as a result. So we move on now to part 2. To be safe, the CPU also needs to know the highest value held in any register during this process so that it can decide how much memory to allocate to these operations. For example, in the above instructions, the highest value ever held was 10 in register C after the third instruction was evaluated. So here, we get to apply a really cool, actually, let's hide that for a second. A really cool symmetry. So fold-L, let's look at fold-L for a second. Fold-L plus, starting with 0, over the list 1, 2, 3, 4. What do you guys think this is going to be? Pause the video if you need some time to think about it. Okay. This is how we implement sum, right? Fold the adding function, starting with 0, over the list 1, 2, 3, 4. And we get 10, of course. But there's this other cool function called scanl in, I guess, data.list? No, it's just in Prelude. Okay. And what does scanl give you exactly? It behaves exactly like fold-L, except that instead of the final value, it gives you a list of all of the intermediate values on the way up. Which is, like, great. It's awesome. You can find uses for it sometimes. It's nice that you don't have to really, like, apply any... you don't have to do anything fancy to change a fold in order to look at the internal states. Whereas, like, suppose that you had written this in, I don't know, Python, let's say, and you had written it as a while loop or a for loop or something. When you wanted to make a change to track all of the values a register had ever had, how would you do it? Well, you'd kind of have to go edit the for loop, right? And make it save, like, at every step, look through the registers and find the largest one and compare them against some other largest value that you're tracking and save the result there if it's larger. And that's not, like, horrible. I mean, it works. It's fine. But it doesn't really compose. You can't take the idea of running the program and the idea of finding the largest anything has ever been. You can't really separate them. They're sort of glommed together into that for loop. Whereas when we have tools like folds and scans, which are just folds where you keep the intermediate values, you can separate those two things, right? We can say, oh, first, please just scan and run the whole program for me and give me back a list of all the states the program was ever in. And then you can look through all the states the program was ever in and make whatever decision you need to, which can be quite simple because it doesn't have to be tied together with all the logic for running a program. So here we have a list of all the states we've ever been in, and what do? Well, first we map a function over it. It occurs to me now, this is just a really dumb way to do it. I'll tell you what I did now, and then we'll fix it. What I did was I said at each step of the program, after running each instruction, I would like to look at all the register elements, and I want to find the largest one. So basically, we're going to return turn our list of states into a list of ints, where each int is like the largest register that currently exists. And so there was a trick, of course, which is that at the very first state, there are no elements at all. No registers have been written to. And so maximum was like, sorry, I can't give you back a value. Your program is broken. And so I was like, ugh, fine. Put a 0 in, like a fake register that's size 0. And then at the end of that, we call maximum on that sort of list of maxes that we got back. And that works. It's fine. I mean, it got me the right answer. But it's actually quite silly. Really, I should just write turn each list of states into a list of register values, combine together all of those lists into one giant list of all the values any register's ever had through running this program, and then compute the maximum of that. That would be much cleaner. And so let's make that change now. We'll just map concat. I always forget if it's called concat map. It's called concat map, isn't it? Concat map. Yes. There. So we basically just say for all the states, map them to produce a list of all the registers that they had, concat all those lists together, and finally call maximum on the result of that. And like that should work. It'll give us the same result. Yeah, 7774, which is indeed the same as the old answer. I don't know. Concat map I find a little bit silly. I would rather just use the more general function bind, which for lists does the same thing. But we've already looked at this before for maybes, and it did something. When was that anyway? Day 5, when we were implementing move. We saw that for maybes, bind takes a maybe on the left and short circuits if that value is nothing, but otherwise pulls a value out of it and then calls the function on the right. That's one thing bind can do. But for lists, it does something different. Bind is part of this really powerful abstraction called a monad. And I'm not going to try to do like a monad tutorial in one episode or anything. I'm just going to like sort of show you guys a few applications of it, and then I don't know, maybe one day I'll try to do a tutorial, although who knows, I don't think it would turn out that well. I think you sort of have to just be exposed to the concept a number of times, and then sort of eventually you maybe start to see how it works. Anyway, so for lists, bind is the same as map concat, or concat map. Map concat? God damn it. I always get it confused because it's backwards in Clojure and in Haskell. In Clojure, it's mapcat, so in Haskell, it must be concat map. For lists, bind is the same as concat map, except it like takes its arguments in a weird order, I guess. So anyway, same thing. What am I doing? I don't want to do that. So let's just let's save this. Git add. Yes, git commit -m. Day 8. What exactly is it that we have done here? We have improved part 2 by removing special case for 0. Sure, I don't know. Something like that. So there you go. That's our I guess we never looked at main. Main is pretty boring. You guys have seen it a million times. Indirect of show composed with both part 1 and part 2, composed with map, parse, and words over all the lines. Like you guys have seen this. It's fine. And we are actually we're ahead of schedule now. Like I could do episode 9 live. I don't think I'll stream it, but I might try to record it starting at 9 and then upload it like tomorrow morning or something. But I want to stream at least one episode, and I don't really know which one. We'll see. Just hold your breath, I guess. Anyway, that's going to do it for this episode, which went quite long, despite it being a simple program and me not actually even showing you how I solved it. Just because I had a lot of like advice, explanations, a lot of stuff to say. I hope you guys don't mind that you didn't get to watch me solve it. I think that I hope that what actually happened was more interesting. But I guess that's something that will vary from person to person. Some of you will wish you had gotten to see me solve it from scratch, but nothing very interesting happened, honestly. this way I get to explain what I'm thinking a lot more clearly because I don't have to balance thinking aloud with like coming up with a clear picture of the program. So I kind of like doing these record post narration, I guess is the right word, maybe. But anyway, I should shut up and just say thanks for watching, and I'll see you next time.